Stephen Hawking was born on January 8th, 1942, in Oxford, England, at a time when the world was still overshadowed by war. London was under threat of bombing, so his mother had traveled to Oxford, considered a safer place for childbirth. It was a beginning shaped by uncertainty, yet also by resilience. His parents, Frank and Isabel Hawking, were both intellectually curious and deeply academic. His father was a medical researcher specializing in tropical diseases, and his mother had studied philosophy, politics, and economics at Oxford during a time when few women attended university. Their household was not wealthy, but it was rich in ideas. Books filled the rooms. Conversations at dinner revolved around science, politics, and abstract questions about existence. From early childhood, Stephen displayed an intense curiosity about how things worked. He was not the neatest or most outwardly disciplined child, but he had a quiet determination beneath his calm demeanor. He enjoyed dismantling mechanical objects to understand their structure. He built model airplanes, invented complicated board games, and constructed small devices from spare parts. The process of figuring something out seemed to fascinate him more than the finished result. When the family moved to St. Albans, north of London, Stephen attended St. Albans School. He was not immediately at the top of his class. His handwriting was messy, his notes minimal, and he sometimes appeared distracted. Yet teachers noticed that when a difficult problem was presented, Stephen's mind would engage deeply. He grasped patterns quickly and preferred reasoning over memorization. Among friends, he was known for his dry humor and inventive mind. He and a small group of classmates attempted to build a rudimentary computer using clock parts, telephone switches, and scraps of electronic material. Though primitive, it demonstrated his growing fascination with systems, logic, and the underlying structure of complex processes. His father hoped he would pursue medicine, continuing the family scientific tradition. Stephen, however, was drawn toward mathematics. Unfortunately, his chosen college at Oxford did not offer a mathematics degree at the time, so he selected physics instead, focusing particularly on theoretical physics, the branch that seeks to describe the universe through mathematical frameworks rather than laboratory experiments. At 17, he entered University College, Oxford. Compared to many of his peers, he studied relatively little in conventional terms. He found much of the early coursework straightforward and relied heavily on intuition. Instead of constant reading, he spent time rowing, socializing modestly, and thinking quietly. Yet beneath this relaxed exterior, his intellectual abilities were sharp. During his final examinations, he reportedly hovered between first-class and second-class honors. When asked about his future plans during a Viva examination, he answered with confidence and wit, making it clear that he intended to pursue cosmology. The examiners awarded him a first-class degree. In 1962, he moved to Cambridge to begin his graduate studies in cosmology. At that time, cosmology was still a developing field. The idea that the universe had a beginning, the Big Bang, was gaining traction but remained controversial. Many scientists still debated whether the universe was eternal and unchanging. Stephen was drawn to the biggest possible questions. Where did the universe come from? Did time have a beginning? Could the laws of physics explain creation itself? Under the supervision of Dennis Sciama, a respected cosmologist, Hawking immersed himself in general relativity, Albert Einstein's theory describing gravity as the curvature of space-time. The mathematics was complex, but it offered a powerful language for describing the structure of the cosmos. It was during this period, in his early 20s, that subtle physical symptoms began to appear. He noticed increasing clumsiness. He stumbled occasionally. His speech sometimes seemed slightly slurred. At first, these signs were easy to dismiss. Graduate life was demanding. Fatigue was common, but the symptoms progressed. Medical examinations followed. Tests were conducted. The diagnosis came with stark clarity: amyotrophic lateral sclerosis, commonly known as ALS, a progressive motor neuron disease. Doctors estimated he might have only 2 years to live. He was 21 years old. The shock was immense. For a time, he withdrew emotionally. The future he had envisioned, one filled with decades of research and discovery, suddenly seemed shortened beyond recognition. Watching his body weaken while his mind remained active was deeply unsettling. Yet something unexpected happened. Rather than surrender to despair, Stephen gradually redirected his focus toward what he could still do. If his time was limited, he reasoned, then he would use it to pursue the most profound questions available. He resumed his research with renewed determination. Around this time, he became engaged to Jane Wilde, a literature student he had met shortly before his diagnosis. Her presence brought stability and encouragement. Their relationship gave him a renewed sense of purpose and emotional grounding during an uncertain period. Academically, Hawking began investigating singularities, points in space-time where density and curvature become infinite. Working alongside mathematician Roger Penrose, he explored the implications of Einstein's equations under extreme conditions. Penrose had shown that collapsing massive stars could produce singularities, regions later understood as black holes. Hawking extended this reasoning to the universe itself. If gravity could create singularities inside stars, could the entire cosmos have begun as a singularity? Their combined work demonstrated that, under reasonable physical assumptions, the universe must have originated from a singular state, a moment when space and time, as we know them, began. This was a profound shift in cosmological thought. The beginning of the universe was no longer purely philosophical or theological speculation. It had mathematical backing within general relativity. As his physical strength gradually declined, Hawking relied more heavily on a cane than crutches. His speech became slower, yet his mind continued moving freely through equations describing black holes, expanding universes, and the origin of time itself. In lecture halls at Cambridge, students listened closely as he described curved space-time and gravitational collapse. His body was beginning to fail him, but his ideas were expanding outward toward the earliest fractions of a second after the Big Bang. In the quiet rooms of the university, surrounded by chalkboards filled with symbols, Stephen Hawking was beginning a journey that would not only redefine cosmology, but also demonstrate something equally powerful: that the boundaries of the body need not define the boundaries of thought. And as the 1960s moved forward, his research would take him deeper into one of the most mysterious regions of physics, the dark, silent edges of black holes, where gravity bends space so completely that even light cannot escape. By the late 1960s, Stephen Hawking's body was weakening steadily, but his scientific ambition was intensifying. He had accepted that ALS would continue to limit his movement, yet he refused to let it narrow his intellectual reach. Instead, he focused his energy on the most extreme environments in the universe, places where gravity becomes so intense that ordinary intuition collapses. Black holes had long been predicted by Einstein's equations of general relativity. They were regions formed when massive stars collapse under their own gravity, compressing matter into extraordinary density. According to classical physics, once something crossed the boundary known as the event horizon, it could never return. Not even light could escape. For many physicists, black holes were mathematical curiosities, strange solutions to equations, perhaps not even real. Hawking approached them differently. He wanted to understand not just their existence, but their fundamental nature. Working within the framework of general relativity, he proved an important result known as the area theorem. It showed that the surface area of a black hole's event horizon can never decrease over time. This result resembled a principle from thermodynamics. Entropy, a measure of disorder, also never decreases in a closed system. The resemblance was striking. Some physicists, including Jacob Bekenstein, began proposing that black holes might actually possess entropy. If so, they might also have a temperature. At first, Hawking was skeptical of this idea. A black hole, by definition, was supposed to absorb everything and emit nothing. How could it possibly have a temperature? But rather than dismiss the question, he examined it carefully. In the early 1970s, Hawking began combining two previously separate branches of physics: general relativity, and quantum mechanics. General relativity describes gravity on cosmic scales, planets, stars, galaxies. Quantum mechanics governs the microscopic world. Particles, fields, fluctuations. These two theories had never fully agreed with one another. Yet near a black hole, both must operate simultaneously. Hawking calculated what would happen to quantum fields at the edge of a black hole's event horizon. In the quantum world, empty space is not truly empty. Tiny particle-antiparticle pairs constantly flicker into existence and vanish almost immediately. Near the event horizon, something subtle occurs. If one particle of such a pair falls into the black hole while the other escapes, the escaping particle would appear as radiation emitted by the black hole itself. In 1974, Hawking announced a result that stunned the scientific community. Black holes are not completely black. They emit radiation. This radiation, now known as Hawking radiation, implies that black holes slowly lose mass over time. Given enough time, they could eventually evaporate entirely. The idea was revolutionary. It overturned the long-standing view of black holes as eternal traps. It also suggested that gravity, thermodynamics, and quantum theory were deeply interconnected. Hawking radiation remains one of the most profound theoretical discoveries of 20th century physics, though it has not yet been directly observed, because the radiation from astrophysical black holes is extraordinarily faint. The mathematics supporting it remains powerful and influential. As his scientific reputation grew, his physical limitations deepened. He increasingly relied on a wheelchair. His speech became more difficult to understand. Yet he continued teaching, supervising students, and collaborating with physicists around the world. Colleagues who met him during this time often remarked on his quiet intensity. His body was nearly motionless, but his eyes conveyed alertness and focus. He could follow complex arguments rapidly, interrupting with precise questions that cut directly to the heart of a problem. In 1979, Hawking was appointed to the Lucasian Professorship of Mathematics at Cambridge, the same position once held by Isaac Newton. It was one of the most prestigious academic chairs in the world. The symbolic weight of the appointment was profound. Centuries earlier, Newton had described gravity as a universal force binding the cosmos. Now Hawking was probing gravity at its most extreme limits, asking what happens when space-time itself breaks down. Throughout the 1970s and early 1980s, he continued exploring a question that would define much of his later work. How did the universe begin? If the Big Bang represented a singularity, a point where physical laws collapse, then what preceded it? Could time itself have emerged from something more fundamental? He began developing what became known as the no-boundary proposal, in collaboration with physicist James Hartle. The idea suggested that the universe might not have a sharp boundary in time. Instead of a singular starting point in the conventional sense, the early universe might be described by a smooth, finite geometry without edges, similar to how the surface of the Earth has no boundary, even though it is finite. In this model, asking what happened before the Big Bang would be like asking what lies north of the North Pole. The question itself might lose meaning. These ideas pushed cosmology into new philosophical territory. Hawking was not only calculating equations, he was reshaping how humanity conceptualized time itself. Then, in 1985, during a visit to Geneva, he developed severe pneumonia. His condition became critical. To save his life, doctors performed a tracheotomy, which permanently removed his ability to speak. For a time, communication became almost impossible. Eventually, he was fitted with a speech-generating device. At first, he selected words by hand. Later, as paralysis progressed, he controlled the system using a small muscle in his cheek. The synthesized voice that emerged would become globally recognizable, mechanical, steady, calm. Though artificial, it carried his thoughts across lecture halls, television screens, and eventually the world. Many might have withdrawn from public life after such a loss. Hawking did the opposite. He continued researching, lecturing, and writing. His condition made movement difficult, but it did not slow his intellectual pace. In fact, the constraints seemed to sharpen his focus further. In quiet offices at Cambridge, surrounded by students and collaborators, he contemplated black hole evaporation, quantum gravity, and the ultimate fate of the universe. While his body grew still, his mind ranged across billions of years, from the first fraction of a second after cosmic birth to the distant future when stars will burn out and galaxies fade. The paradox of his life became increasingly visible, a man almost entirely immobilized, yet exploring the most dynamic and expansive questions imaginable. And as the 1980s progressed, his work would reach beyond academic journals and into the wider public imagination, bringing the mysteries of the universe to millions who had never before considered black holes or the origin of time. By the mid-1980s, Stephen Hawking was no longer known only within academic circles. His scientific work on black holes and the origin of the universe had already secured his place among the leading theoretical physicists of his generation. But now, something unusual began to happen. The wider world started listening. In 1988, he published A Brief History of Time. The goal of the book was ambitious: to explain the structure, origin, and fate of the universe in language accessible to general readers. Cosmology is filled with equations, curved space-time diagrams, and abstract mathematics. Hawking deliberately minimized equations, choosing instead to guide readers conceptually through ideas such as the Big Bang, black holes, imaginary time, and the search for a unified theory. Few expected the book to succeed commercially, yet it did. It remained on bestseller lists for years and was translated into dozens of languages. Millions of people who had never studied physics found themselves contemplating singularities and cosmic expansion. Hawking had done something rare. He made the deepest scientific questions feel both vast and personal. His computer-generated voice, calm and slightly metallic, became part of his public identity. Interviews, documentaries, and lectures carried that distinctive tone across the globe. The contrast between his nearly motionless body and the cosmic scale of his ideas created a powerful image, a mind roaming freely through space and time. But even as he became a cultural icon, Hawking continued wrestling with difficult theoretical problems. One of the most troubling issues in physics emerged from his own discovery of Hawking radiation. If black holes slowly evaporate, what happens to the information about the matter that fell into them? Quantum mechanics states that information cannot be destroyed. Yet if a black hole disappears completely, where does that information go? This became known as the black hole information paradox. For decades, Hawking argued that information might truly be lost, that black hole evaporation erased it from the universe. This position challenged a core principle of quantum theory and sparked intense debate among physicists. The paradox was not just technical. It pointed toward a deeper incompatibility between general relativity and quantum mechanics. One theory described gravity and space-time on large scales. The other governed particles and probabilities on the smallest scales, reconciling them into a single framework, often called a theory of quantum gravity, became one of the greatest challenges in modern physics. Hawking remained at the center of that search. Throughout the 1990s and early 2000s, he continued publishing papers and collaborating with leading theorists. Despite increasing paralysis, he attended conferences, sometimes traveling internationally. Assistants helped manage the complex technology that allowed him to communicate, but the ideas themselves remained entirely his own. He also maintained a playful sense of humor. He appeared on television programs, including popular sitcoms, allowing himself to be portrayed with self-awareness and wit. He joked about time travel parties and extraterrestrial visitors. His humor softened the intimidating scale of his subject matter, reminding audiences that even the largest questions could be approached with curiosity rather than fear. In 2004, after decades of debate, Hawking publicly revised his position on the information paradox. He announced that information is not lost in black holes after all. Instead, he suggested that subtle quantum effects allow it to escape in highly scrambled form within Hawking radiation. The announcement demonstrated something important about his character. He was willing to change his mind when evidence and reasoning demanded it. For a scientist whose name was attached to one of the central ideas in the debate, this shift required intellectual humility. Meanwhile, his personal life evolved in complex ways. His marriage to Jane ended after many years, and he later remarried. The strain of long-term illness, global fame, and academic pressure created challenges. Yet through it all, he remained committed to scientific work. He often spoke about the fragility of humanity. He warned of risks such as climate change, nuclear war, and artificial intelligence mismanagement. He advocated for space exploration and the long-term survival of human civilization beyond Earth. To Hawking, understanding the universe was not only a matter of curiosity, but of perspective. Seeing Earth as a small planet orbiting an average star encouraged humility and responsibility. As his muscles weakened further, even the small cheek movement used to operate his communication device became slower. Engineers worked continuously to adapt new technologies, ensuring he could still select words and construct sentences. The pace of his speech device meant that every sentence required patience, yet that slowness often gave his words added weight. Each phrase felt deliberate. He once reflected that his disability had likely helped his career in theoretical physics. Because he could not perform experimental work or move easily, he focused entirely on abstract reasoning. His physical stillness, paradoxically, concentrated his mental energy. Through decades of progression, ALS never silenced his curiosity. In lecture halls, on television screens, and within research papers, he continued to explore the same profound themes: the beginning of time, the behavior of black holes, and the ultimate fate of the cosmos. The image of Hawking gazing slightly upward from his wheelchair became symbolic, as though he were looking not at the room around him, but beyond it, toward galaxies billions of light years away. And as the new century advanced, he remained engaged in the deepest unsolved puzzle of modern physics. How to unite the laws governing the very large with those governing the very small, to discover whether the universe ultimately operates under a single, coherent principle. Even as his body approached its limits, his thinking moved toward boundaries far beyond Earth, toward the edges of time itself. As the years moved forward, Stephen Hawking's presence became something larger than that of a scientist alone. He had become a symbol of endurance, of intellect unconfined by physical limitation, and of humanity's relentless desire to understand the cosmos. By the 2010s, his body was almost entirely paralyzed. Communication required immense patience. Each sentence was formed by selecting letters through a minute movement in his cheek, detected by infrared sensors and translated into speech by a computer. Conversations unfolded slowly, yet the ideas carried within them remained expansive. He continued to work at the University of Cambridge, surrounded by students, collaborators, and assistants who helped translate his thoughts into equations and publications. Despite increasing medical complexity, he maintained a schedule of research, writing, and public engagement. He never lost his fascination with the origin of the universe. In his later years, he revisited questions about the Big Bang and the nature of time. He explored whether the universe might be one of many, part of a broader multiverse. He examined how quantum fluctuations in the earliest moments of existence could have shaped the large-scale structure of galaxies we observe today. His thinking remained bold. He was willing to speculate carefully, to stretch theoretical boundaries, while still grounding his ideas in mathematics. For Hawking, the ultimate goal was clear: to discover a unified theory that could describe all fundamental forces, gravity, electromagnetism, and the quantum forces within a single framework. He often referred to this as understanding the mind of God, not in a religious sense, but as a metaphor for complete comprehension of the laws governing reality. Beyond physics, he reflected deeply on humanity's future. He warned that technological power must be matched by wisdom. Artificial intelligence, genetic engineering, climate instability, and nuclear weapons posed risks that required global cooperation. He encouraged space exploration as a long-term safeguard for human survival. believing that spreading beyond Earth could protect civilization from planetary catastrophes. At the same time, he retained a sense of wonder. He spoke about the beauty of a night sky, about the extraordinary improbability that conscious beings could emerge from simple physical laws. He reminded audiences that while we may be small in cosmic scale, our capacity to understand the universe gives our existence meaning. On March 14, 2018, Stephen Hawking passed away at his home in Cambridge. The date carried quiet symbolism. It was Pi Day and also the birthday of Albert Einstein. He was 76 years old, far surpassing the prognosis given at age 21. Tributes came from across the world. Scientists honored his contributions to cosmology and black hole physics. Leaders praised his resilience. Ordinary readers remembered how his books had opened their minds to vast, unfamiliar ideas. Later that year, his ashes were interred at Westminster Abbey, placed between the graves of Isaac Newton and Charles Darwin. The location formed a symbolic line through history, from Newton's laws of motion to Darwin's theory of evolution, to Hawking's exploration of space-time and singularities. It was a fitting resting place. Newton had unified the heavens and the earth through gravity. Darwin had explained the diversity of life through natural selection. Hawking had probed the beginning of time and the fate of black holes. Yet perhaps his greatest legacy extends beyond equations. It demonstrated that intellectual freedom does not depend on physical strength, that curiosity can outlast limitation, that even when the body grows silent, the mind can still speak across continents and generations. Through a synthetic voice and a wheelchair, he invited millions to look upward, to consider galaxies, event horizons, and the birth of the cosmos. He transformed abstract mathematics into shared human wonder. In contemplating black holes, he revealed that even the darkest regions of space may emit light. In facing illness, he revealed that even the most fragile body can house extraordinary determination. The universe he studied is vast, stretching billions of light years in every direction. Stars ignite and fade. Galaxies collide. Time itself unfolds across unimaginable scales. Yet within that immense expanse, a single human mind was able to ask where it all began and how it might end. Stephen Hawking's life reminds us that while we are small in the cosmic story, we are also participants in it. We are made of the same atoms as distant stars. We exist within the same laws he sought to understand. And through quiet persistence, through thought carried on a mechanical voice, he showed that understanding the universe is not reserved for the strong or the unburdened. It is available to any mind willing to ask the deepest questions and follow them wherever they lead.